Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a very good morning to everyone. So in this video, I will continue lecturing on chapter 3 of Advanced Thermodynamics, Pure Substance, part 2. Previously in part 1, we have introduced the concept of pure substance, number of property substance may have, and discussed the physics of phase change processes. And we also already illustrate the PV, TV and PT property diagrams and PVT surfaces of pure substance. In chapter 3 part 2 video, we will demonstrate the procedures for determining thermodynamic properties of pure substance from tables of property data. Okay, you will learn on how to read table of property data. We will describe the hypothetical substance ideal gas and the ideal gas equation of state. After that, we will apply the ideal gas equation of state in the solution of typical problems and introduce the compressibility factor, which accounts for the deviation of real gases from ideal gas behavior, and then we will present some of the best known equations of state. Okay, so for recap, let's see a video on property diagrams for phase change process.
In this spoken tutorial, we will try to understand PVT surface for pure substance that contracts on freezing by the help of a 3D model made in AutoCAD. Prerequisites for understanding of this spoken tutorial are a thorough understanding of properties of pure substance, PV diagram of pure substance, TV diagram of pure substance, PT diagram of pure substance, and definition of basic terms relevant to behavior of a pure substance. This is the 3D model of PVT surface for a pure substance that contracts on solidifying. It is clear from 3D model that pressure, specific volume and temperature are plotted on three mutually perpendicular axes. This whole is the PVT surface of the pure substance that contracts on freezing. And the significance of PVT surface of a pure substance is all possible equilibrium states of the pure substance are represented by a point on this PVT surface of the pure substance. Let me now start the explanation of model of PVT surface of pure substance, first by explaining different surfaces involved in the making of this model. The green colored surface TUVY indicates various possible equilibrium states of the pure substance when it is in solid phase. The orange colored surface PCILMJS indicates various possible equilibrium states of the pure substance in liquid state. One thing I would like to add here is at pressures higher than critical pressure, the differentiation between gas and liquid should not be taken very seriously, because at pressures more than critical pressure for a pure substance, liquid and vapor phase never coexist in equilibrium, and we can call the pure substance simply a fluid. The cream colored phase RAGKLHBQ indicates various possible equilibrium states of the pure substance in vapor phase. Here I would like to add one thing, that the boundary line between vapor and gas should not be taken very seriously, because gas is simply a name for superheated vapors. The yellow colored surface KNWXOMLK indicates various possible equilibrium states of the pure substance in gaseous state. The light blue colored phase PSTU indicates various possible equilibrium states of the pure substance when it is in two-phase solid liquid region. The dark blue colored surface RQUVR indicates various possible equilibrium states of the pure substance when it is in the two-phase solid vapor region. The pink colored surface QBHLICPQ indicates various possible equilibrium states of the pure substance when it is in the two-phase liquid vapor region. Lines of constant temperature plotted on PVT surface are called isotherms. On the 3D model of the PVT surface of the pure substance, you can see the isotherm A, B, C, D, E, F. You can see the isotherm G, H, I, J. You can see the isotherm K, L, M, and you can see the isotherm NO. LICP is called the saturated liquid line and LHBQ is called the saturated vapor line. Let me now develop a connection between 3D model of PVT surface and 2D PV diagram, PT diagram and TV diagram. The PT diagram for pure substance that contracts on freezing is shown here. This is the axis of pressure, this is the axis of temperature. This is solid phase area, this is liquid phase area, and this is vapor phase area. And if you look at the model of PVT surface from right side, you will see the PT diagram. Let me show it to you. Suppose this is front direction of looking, this is top direction of looking, and then this direction will be right direction of looking. And when you look at the 3D model of PVT surface from right side, you see that it appears similar to the PT diagram. This is the axis of pressure, this is the axis of temperature, this is the triple point, this is the critical point, this is the solid region, this is the liquid region, this is the vapor region. Once more, I have brought the slide of PT diagram on screen so that comparison becomes very clear in your brain. This is the PV diagram for pure substance that contracts on freezing. This is axis of pressure, this is axis of volume, this is the critical point, and these are isothermals plotted on the pressure volume diagram. If you look at our 3D model of PVT surface from front direction, it will appear same. Let me now demonstrate it. Now you are looking at the 3D model of PVT surface from front direction, and its view is same as the PV diagram shown in the slide. I am bringing slide once more on the screen so that comparison becomes very clear. Similarly, if you want to see the TV diagram of pure substance, you will simply look this 3D model of PVT surface of pure substance from top. Let me look at this model from top. This is the axis of temperature and this is the axis of specific volume. And this is the TV diagram for a pure substance. Let us now try to understand behavior of pure substance by the help of 3D model of PVT surface for pure substance that contracts on freezing. Let us start by isotherm On. For isotherm On, temperature is more than critical temperature and therefore we can call the pure substance to be a gas. If temperature is more than twice the critical temperature, then gas starts behaving as an ideal gas, and in that case isothermal On will be a rectangular hyperbola. Isotherm KLM is the critical isotherm. State point L gives us the value of critical pressure, critical temperature, and critical specific volume for the pure substance. At critical point, saturated liquid and saturated vapor states are identical and there is no latent heat of vaporization, or we can say latent heat of vaporization is zero at critical point. Isotherm A, B, C, D, E, F represents temperature higher than triple point temperature but lower than critical temperature. At state point F, the pure substance is in solid state. As pressure reduces, there is a very little increase in specific volume until we reach the state point E where the melting starts. ED is constant pressure, constant temperature melting process in which change of phase from solid to liquid takes place until D is reached. At D, the melting process gets completed. On further decrease of pressure, there is very little increase in specific volume until state C is reached. CB is constant temperature, constant pressure vaporization process in which change of phase from liquid to vapor takes place. B2A represents superheated vapor region. Let us now try to understand how triple point appears in a 3D model for PVT surfaces. Triple point of pressure temperature diagram appears as a triple line in the PVT surface model. The reason is for triple point the pressure is fixed and temperature is fixed. Specific volume varies depending on proportion of each phase. This is the sublimation line in the PT diagram and let us observe how it appears in the PVT surface model. It is interesting to observe that the sublimation line appears as a surface RQUV in the PVT surface model. There are a lot more things to be covered, but since there is time limit for spoken tutorial, I stop here. Thanks for watching.
Okay, so now the PVT surfaces present a great deal of information at once. But in thermodynamic analysis, it is more convenient to work with two-dimensional diagrams such as PV and TV diagrams. Just now you have watched a video that explaining on the PVT diagrams. It's in 3D diagrams, but then it is easier to just look at it separately, PV and also TV diagrams. Alright, so property tables. Let's continue on the next subtopic. It's 3.5 property tables. For most substances, the relationship among thermodynamics properties are too complex to be expressed by simple equations. Therefore, properties are frequently presented in the form of tables. Okay, it is already done for you. It's already calculated for you, okay, and it is summarized in a form of table. Some thermodynamic properties can be measured easily, but others cannot and are calculated by using the relation between them and measurable properties. The results of these measurements and calculations are presented in tables in a convenient format. Okay, let's see. Okay, this is saturated liquid and saturated vapor states. Table A4, okay, table A4, you can see in the appendix of thermodynamics book. Saturation properties of water under temperature, okay, for temperature. And then it means when temperature value is given. So in the question, if the temperature is given, then you have to refer to table A4. Then table A5, saturation properties of water under pressure. If in the question they gave you the pressure, the value of pressure, then you have to look at table A5. Okay, VF means specific volume of saturated liquid. Okay, VG, specific volume of saturated vapor. VFG, difference between VG and VF. Okay, they already calculated it for you. What is HFG? HFG is enthalpy of vaporization or latent heat of vaporization. Means the amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure. It decreases as the temperature or pressure increases and becomes zero at the critical point. Okay, this is just a partial list of table A4. Here you can see it is the temperature is given at the left side of the table. So if it is in temperature, then it is table A4. Okay, then you can see saturated liquid VF, saturated vapor VG. At the right hand side, you will see VFG, you will see HFG, HF, HG, HFG. Okay, that you can refer to the table by yourself. All right, so yeah, this is the example of the TV diagram. Here is the given temperature, saturation pressure, saturated liquid, okay, VF, VG, UF, UFG, internal energy, enthalpy, and also entropy. Okay, you can refer to this table. All right. Yeah, this is the continuous table. 200, 205. Then this is PV diagram, table A5. Given property is pressure, okay, at the left hand side is pressure, then it is table F5, then it is the same. You have specific volume, internal energy, enthalpy, and also, okay, SFF, saturated liquid, evaporation, and saturated vapor. Alright, so now, during a vaporization process, a substance exists as part a liquid and part vapor, means it is mixture of saturated liquid and saturated vapor. How to analyze this mixture? Know the proportion of liquid and vapor phase in the mixture and then defining quality. So, you already understand at below this dome, okay, it is saturated vapor liquid mixture. So the liquid and vapor coexist in equilibrium. Okay, but then how to analyze this mixture? How much proportion of liquid? How much proportion of vapor? Okay, so in order to know that, to calculate and analyze that, you have to define the quality. Okay, how to define quality? Okay, quality X equal to the ratio of the mass of vapor to the total mass of the mixture. X equal to M vapor over M total, where M total equal to M liquid plus M vapor equal to MF plus MG. Then you can calculate using this equation. Mg equal to Mg over Mf plus Mg. Okay, and this quality is between 0 to 1, where 0 is saturated liquid and 1 is saturated vapor. Okay, this quality is related to the horizontal distances on PV and TV diagrams. Here, you can see it here. X equal to VAVG minus VF. Okay, VAVG minus VF over VFG. Okay, the VFG value of a saturated liquid vapor mixture lies between the VF and VG values at the specified T or PV diagram. Alright, so here we already see the equation for quality. X equal to M vapor over M total. And then we can calculate the specific volume, VAVG, internal energy, UAVG, and also enthalpy, HAVG, from these equations. Okay, please remember these equations. Okay, and also please take note on the SI unit for each of these property. Okay, so these kind of questions will come out during the examination. Okay, the calculation of quality, the enthalpy, or even specific volume. Okay, so now let's see the definition of enthalpy. Enthalpy, a combination property. Okay, enthalpy with the symbol H, uppercase H, is from the Greek word enthalpion, which means heat. It's a property. It is defined as the sum of the internal energy U and the boundary work PV. It can be simplified as heat content per unit amount of extensive case. Okay, enthalpy H equal to internal energy U plus boundary work PV. Then we can simplify the equation to H equal to U plus PV, kilojoule per kilogram. Okay, this is the specific enthalpy. And then enthalpy H equal to U plus PV, the unit is kilojoule. Okay, this is the product pressure times volume. Okay, PV has an energy unit. Okay, you can see the unit SI, the conversion of unit SI here. Okay, please remember this conversion. Alright, so enthalpy of formation is the enthalpy of a substance at a specified state due to its chemical composition. The enthalpy of formation of all stable elements has a value of 0 at the standard reference state of 25 degree and 1 atm. Okay, some of the types of enthalpy. First, enthalpy of formation always have a 0 at standard reference state of 25 degree and 1 atm. How about enthalpy of reaction, HR? Okay, it is defined as the difference between the enthalpy of the products at a specified state and the enthalpy of the reactants at the same state for a complete reaction. And then we have enthalpy of vaporization, HFG, that is written in the table 4 and 5, okay, or also called as latent heat of vaporization. It is the amount of energy needed to vaporize a unit mass of saturated liquid at a given temperature or pressure, and it is the quantity listed in the saturation tables that I explained before. Okay, so now linear interpolation 3.7. What is linear interpolation? Okay, what happened if your temperature or pressure did not match provided table? For example, we have table F4 here, 85, 90, 95. Okay, let's say a given temperature in the question is 92 degree. Determine pressure, specific volume of liquid and vapor, Vf and Vg. So we don't have given temperature 92 degree in this table. So how can we calculate this kind of question? The answer is we do the linear interpolation. Okay, how to calculate linear interpolation? Suppose that y equal to fx only and you are given x equal to x star and want to find y equal to y star from a table. First, find the closest values above and below x star. Okay, x star, for example, 92 degree. Okay, and then y star, you want to calculate y star. Then find the closest values above and below of x star. So the question asks you 92 degrees. So the closest values are 90 and 95. So 90 will become x1, 95 will become x2. Okay, and then y1 is 70.14 kilopascal, y2 is equal to 84.55 kilopascal. Then you calculate it like this, using this equation of linear interpolation. X star is 92 minus 9 x1, 90 degree, and then x2 is 95 minus 90 degree. Okay, equal to y star, you don't know this, okay, minus y1 70.14 over y2 84.55 minus 70.14. Then you will get x and you will get y star. Alright, same goes with other property. Okay, you can just use this one x, and then y you can use for other properties, not only saturation pressure, but you also can calculate for saturated liquid, saturated vapor. Okay, now subtopic 3.8, ideal gas equation. Okay, property tables provide very accurate information about properties. However, it is unpractical. Okay, so we want to have a practical and desirable approach where simple relations among general properties. So, any equation that related to pressure, temperature, and specific volume of a substance, we can call it as equation of state. The simplest and best known equation of state for substances in the gas phase is the ideal gas equation of state, or we call it as ideal gas. This equation predicts the PVT behavior of a gas quite accurately within some properly deselected region. Okay, the equation for ideal gas equation of state or ideal gas relation or ideal gas, this is their name, okay, is equal to PV equal to RT. P pressure, okay, V specific volume equal to R gas constant and T absolute temperature. Alright, so different substances have different gas constant. Okay, this one. This part, okay, has different gas constant following different substances. Okay, then you can get R equal to this values. Okay, depends on the question. If it's using universal gas constant, then Ru. Okay, Ru for each substance. If they give you the molar mass, then you need to calculate the gas constant. Alright, molar mass can be defined as the mass of 1 mole, also called a kilogram mole, kg mole in kilograms. Example, molar mass of nitrogen is 28. So M equal to 28 kilogram per kilomole equal to 28 lbm, lbmol. Okay. The mass of a system M is equal to the product of its molar mass and the mole number. You also can calculate the mass of the system by using this equation, M equal to M times with N, okay, mole number. Values of R and M for several substances is given in table A1. Okay, you also can refer the all calculated values of R and M in table A1. You can refer it by yourself. Okay, so ideal gas equation, okay, you have, I already summarized it here. V equal to MV, then PV equal to MRT. Using molar mass, Mr equal to MNR equal to NRU. Okay, so PV NRUT. Okay, so actually these equations are following what type of question that you ask. Okay, if the question use molar mass, then you have to use equation calculated using molar mass. Okay, then molar specific volume, volume per unit mole is V bar. Okay, V bar, okay, using for this equation. Properties per unit mole are denoted with a bar on the top. Okay, remember properties per unit mole are denoted with a bar on the top like this. Alright, so ideal gas equation at two states for a fixed mass. Okay, if you have two states, then you can calculate it like this. PV over T, P1 V1 over T1 equal to P2 V2 over T2. An ideal gas is an imaginary substance that obeys the relation PVT. It has been experimentally observed that the ideal gas relation given closely approximates the PVT behavior of real gases at low densities. Okay, low P, high T. Alright, so now, is water vapor an ideal gas? At pressures below 10 kilopascal, water vapor can be treated as an ideal gas, regardless of its temperature, with negligible error less than 0.1%. However, at higher pressure, the ideal gas assumption yields unacceptable errors, particularly in the vicinity of the critical point and the saturated vapor line. Okay, here. In air conditioning applications, the water vapor in the air can be treated as an ideal gas. Why? Okay, because in steam power plant applications, the pressure involved are usually very high. Therefore, ideal gas relation should not be used. Okay, so now compressibility factor, a measure of deviation from ideal gas behavior. The ideal gas equation is very simple, thus convenient to use. However, gases deviate from ideal gas behavior significantly at states near the saturation region and the critical point, like we explained before. This deviation from ideal gas behavior at a given temperature and pressure can accurately be accounted by using the compressibility factor. Okay, so compressibility factor is used. Okay, the equation is used to calculate. Okay, calculate the deviation from ideal gas behavior from the question. Okay, from the what they give you. Is Z equal to PV over RT or Z equal to V actual over V ideal. Gases follow the ideal gas equation closely at low pressures and high temperatures. However, what exactly define the low pressure and high temperature? Is 100 degrees high temperature? We don't know that. Okay, that's why we need to calculate the critical pressure and critical temperature. Okay, So in order to calculate that, you have to use this equation. PR is reduced pressure, TR reduced pressure, VR is pseudo reduced specific volume. Then you can use the critical temperature and critical pressure in order to calculate the reduced specific volume, temperature and pressure. Okay, using these equations. Okay, so this is the graph comparison of Z factors for various gases. You can see it by yourself. Okay, then actually we have finished on chapter 3, okay, where we already learned some of important subtopics in chapter 3, especially about the ideal gas, okay, and also the compressibility factor, the linear interpolation. What is the definition of ideal gas itself? Okay, so in chapter 3, overall, we have finished about pure substance and its properties. Okay, so after we finish this chapter, you will continue with chapter 4, 5 and 6 with Dr. Yusri. Okay, I believe he will explain it to you, brief about his lecture on the second week, okay, of the course. Okay, so after you finish watch this chapter 3, you have to submit an assignment, and also I already assign you a test, not a test, it's like a quiz, and you have to submit it before the end of 22nd November 2020. Okay, guys, thank you so much for listening to my videos. I hope you can make a revision and also back up, add your knowledge of advanced thermodynamics by reading the thermodynamics books by yourself. Okay, not only depends on the video itself. Okay, thank you so much. Assalamualaikum warahmatullahi taala wabarakatuh.